we are starting chapter 10, our final full chapter of the school year. And everybody, I'm sure, is really excited about that. The part that I find interesting is that we do a lot of stuff that has to do with probability and display, and it's kind of a nice one to end on. So the rest of the year will be spent in those kind of categories. All right, so if we talk about what you can see currently on there, we've looked in the past at collecting data that was numerical, and now we're also going to talk about collecting data that is categorical. So like, what category do you fit into if I give you choices? Now, they talk about the choices being mutually exclusive. So that means you have to only fit into one or the other, but you could say yes to both. So for example, when you go to a cookout, do you have hamburgers, hot dogs, both, or neither? So in this case, you would have a section for hamburgers only. You'd have a section for hot dogs only. You'd have a section for the people that pick both hamburgers and hot dogs. And then outside of those overlapping circles, you would have the people who pick neither hot dogs nor hamburgers. So we're going to look at some specific categorical data to put into a Venn diagram. FAM is conducting a survey for the school newspaper. He surveyed 175 students at his school and found that 28 students had the new Pi phone. 44 students had a laptop computer and 110 students had neither. Draw a Venn diagram to represent this data and use the given information to figure out how many students are represented in each region. So the first thing that we would look at would be that there's 175 students total. So I am first going to take away the 110 students that have neither, and I'm going to put them outside of the circles because I don't have to worry about them being in any of these three regions. That leaves me with 65 students who have a Pi phone, a laptop, or possibly both. Then it says that 28 students had a Pi phone and 44 students had a laptop. Well, if I add those numbers together, I get 72, which is a problem because there's only 65 kids left. That means the difference between the 72 and the 65, which is a difference of 7, there are 7 kids that are getting counted twice. 7 kids who have both a Pi phone and a laptop, and they need to go in that middle section. So it says, how did you determine the number who have Pi phones and laptops? There is an overlap of 7. So once I take those 7 kids out, the Pi phone circle has to have a total of 28, but 7 of them are in the overlap, leaving the other 21 to have Pi phones only. So you'll notice 21 have Pi phones only, 7 are in the double, altogether 28 are in the Pi phone circle. Now laptops, there have to be 44. So if I take away those 7 kids out of the 44, that leaves 37 who have only a laptop, where 7 have both. The laptop circle altogether, if I add the 37 and the 7 together, have the 44 we wanted and the 110 on the outside. Now you could grab a calculator at this point and add 21 plus 7 plus 37 plus 110, and that should give you the 175 students total. How many students have Pi phones or laptops? Now that's an interesting question because this word or, can I have Pi phone only? Yes. Can I have a laptop only? Yes. Is it possible to have both? Yes. That kid, or in this case, those 7 kids who have both, still fit into Pi phones or laptops. They just happen to have both. So that means all 65 kids who are in the circles are both. How did you find this? That's the 175 kids. Take away the 110 who have nothing, have neither of those options. The remaining 65 are the kids who have a Pi phone or a laptop. This is called an inclusive or, meaning it's possible to do both. Recall that 28 students had the new Pi phone and 44 students had a laptop. Why can't you just add 28 plus 44 to get the answer to part C? Well, we've said before that there were 7 students getting counted twice. We can't count a student twice. That 7 in the double overlapping region represents the fact that those 7 kids fall into both of the mutually exclusive categories. Raul said he could not figure out how to put the data from problem 10-1 into a Venn diagram because it was hard to find the number of students with both Pi phones and laptops. So he put the information into a table like the one below. All right. So he knew that there were 28 kids who had Pi phones. So you'll notice there's a row here for Pi phones that adds up to 28. There's also a row for no Pi phones. And we know there's 110 kids who have no Pi phone and also have no laptop. So those were two numbers that were given in the question. If you go down in the columns, we know that there were a total of 44 kids who had no laptop. I apologize. There are 44 kids who do have a laptop. And in the second column, we have 110 kids still that have no laptop and no Pi phone, but we don't know the total. The total of the entire group is 175. So the first thing we do when we do one of these two-way tables is we plug in all the numbers that we know from the question. Then we start saying, well, what are the things that we can get by adding? So I have a 175 total, meaning 28 Pi phone kids plus all the no Pi phone kids has to add up to 175. So if I fill in the blank here using subtraction, there's 147 total kids with no Pi phone. I can do the same thing down here. 44 kids have a laptop. How many do not have a laptop? Has to add up to 175. Using subtraction, I can get that is 131. Then with those two numbers, I can start to fill in numbers inside the table. The kids with a laptop but no Pi phone plus the 110 has to add up to 147. That's 37. Going down, the no laptop but has a Pi phone plus the 110 has to add up to 131. So using subtraction, that missing number is 21. And last but not least, this number here, these are your double overlap. These are your kids that have the laptop and the Pi phone. So across needs to add up to 28. So that would be a 7. And down, the 7 and the 37 has to add up to 44. So all of the numbers work. That's what we're looking for. It's a little bit like solving, the brain puzzles where you're trying to fill in the boxes of numbers 1 through 9. Where can this number go? Where can this number go? And this is very similar. It's all about rows adding up and columns adding up. Complete Raoul's table to find out the number of students in the missing cells. We've done that. This type of table is called a two-way table and is often used to organize information and calculate probabilities. It is called a two-way table because it has two blank. It has two. Now, some people will say mutually exclusive categories, which is true. We can also think of it as having two variables. Two things that can change, two things that can be plugged in or substituted. All right. If we assume that FAM's survey is from a random sample of students in his school, what is the probability that a student in his high school has a Pi phone or a laptop? Okay, so we can look at, this was the two-way table from the front, and this was the Venn diagram from the front. So if we want to look at the probability that a student in his school has a Pi phone or a laptop, we got that number by adding up the 21, the 7, and the 37. We had 65 kids total that were inside the circles. And that's out of how many kids? Like how many kids were total in the survey? There was a total of 175. So we can say we added up the 7 kids and the 21 kids and the 37 kids and divided it by the total 175 to get approximately 37.1% of kids have either a laptop or a Pi phone, or in this case, they could have both. The next question that's on there says, what is the probability that a student has a Pi phone and a laptop? Now, those were the kids in the overlap. So the 7 in the center of the Venn diagram, it's also the 7 kids here that were under laptop and across from Pi phone. That would be 7 kids out of 175, or approximately 4% of the population. Is there an association between owning a laptop and owning a Pi phone? In other words, if you own a laptop, are you more likely to own a Pi phone? So when we do these kind of questions, you want to not be looking at your Venn diagram and you want to be focusing on your two-way table. The really important phrase in here, I'm going to move this down, says, in other words, if you own a laptop. So we are exclusively looking at the column of data that has laptop at the top because we're saying if you own a laptop. So we're only looking at these 44 kids who own a laptop. If you own a laptop, are you more likely to own a Pi phone? So that would be 7 kids out of 44, or approximately 16% of the kids own a laptop. Now, we are comparing that to the kids who have no laptop. So the kids who have no laptop would be 21 kids out of, now again, we're only looking at the no laptop column, out of 131, and that is also approximately 16%. So what we would say is there doesn't appear to be an association between laptop owners versus non-laptop owners owning a Pi phone. So does not appear to be an association. And that's because they both came out to approximately 16%. So it doesn't look like owning a laptop means you have a better chance or a worse chance of owning the Pi phone. Investigate this question by calculating the probability that a laptop owner owns a Pi phone versus a non-Pi phone, and we got 16% for both of those. There are 145 students enrolled in the senior level fitness class at Cooper High School, 116 boys and 29 girls. 24 of the boys and 7 of the girls earned A's for their first semester. Complete the two-way table at the right to display the counts, number of students in each category. So what I would do is I would say, first of all, Cooper High School has 116 boys and 29 girls. That's going to be your total number of boys and total number of girls. 116 boys, 29 girls. Then you also want to look at 24 of the boys and 7 of the girls earned A's. So that's going to be up here, boys and girls who earned A's. So that would be 24 boys who earned an A and 7 girls who earned an A. Complete the two-way table first. So before we do anything else, we need to fill in the rest of the data. Excuse me. So filling across, total number of people who earned an A is 31, right? 24 plus 7. Now, if we go down, 24 plus what number adds up to 116? I can use subtraction to find that 92 boys did not earn an A. And I can use subtraction for girls to find that 22 girls did not earn an A. Now I can add across and get that there were a total of 114 people who did not earn an A. And then down here, how many total people were in this class? I can either add up the 31 and the 114, or I can add up the 116 and the 29. Both have to add up to the same number, and in this case, it's 145. Probability that you're a girl who earns an A. So in order to get that, you have to go down the girl column, because you're kind of saying, if you're a girl, what's the probability you earn an A? So that would be 7 girls out of 29 girls. And if I say 7 girls out of 29 girls, it's approximately 24%. So 7 out of 29, or approximately 24%. What's the probability that you're a boy who earns an A? So now I'm only going to look at the data in the boy column, which would be 24 boys out of 116 boys. And that one is 24 boys out of 116 boys. That's approximately 21%. Is there an association between gender and the grade received? We would say yes. Notice that the percents did not come out to be the same. If yes, is the association strong, moderate, or weak? They're still pretty close, 24 and 21, and it's not a very large class. So we would say the data appears to be weak. A girl is slightly more likely to get an A. And also with data this small, that's really, really hard to say whether or not it's a big enough set of data to be true across the board. Now, you can also fill in this table, which is a table for percents. So we found out that boys getting 21% of the boys getting A's, and boys not earning an A would be the other 79%. Girls earning an A was 24%. The other girls not earning an A, 76%. The columns should add up to approximately 100%. This one we did out of the 116 boys. This one we did out of the 29 girls. That's really important that the data is in columns unless you are asked otherwise. And this one you were very clearly asked if you were a girl, and then A came second. So if you were a girl, what's the probability you got an A? So that told you were working in the girl column. This one said, if you were a boy, what's the probability you earn an A? That told you were working in the boy column. Comparing percents is easier in a relative frequency table that displays percents instead of counts. And we've entered our percents into the relative frequency table. Note that often totals are not included in relative frequency tables. So you don't have to put numbers down here. I'm putting my little explanation so that you can go back and understand where my percents came from. 10-5. A researcher suspected that some blood types are more susceptible to the DAPT genetic defect than other blood types. The researcher collected the following data to investigate. Make a relative frequency table to determine whether there is an association between blood type and the presence of the DAPT defect. So this is your original set of data, and it's number of people in millions. This is not anything to do with percents. This is number of people. So these has DAPT numbers are less than 1 million, whereas the no DAPT numbers are in the millions. So we would want to calculate the total or the sum of each column. This one is 0.68. This one is 311. Now we need those numbers in order to come over here and make that relative frequency table. So this has DAPT and type O blood. That's the 0.30 out of the 0.68. So 0.30 out of 0.68, that's going to be about 44%. Now, I'm not going to fill all of them in this way, but I want you to be able to see where I'm getting the numbers from. So this one is 0.28 out of the 0.68 total, or approximately 41%. This one's approximately 10% and approximately 4%. Now, if you add those up, you get approximately 99%, and that's just because all of the numbers rounded down slightly, but you should be about 100%. The no DAPT column would be the 137 with type O out of the 311 in that column, or approximately 44%. The next one, type A, would be the 131 out of the total 311 in that column, which is about 42%. Then you've got about 10% and about 4%, adding up to approximately 100%. Now, if we want to compare those and say, is there an association between like blood type and whether you have DAPT or no DAPT? These percentages are either identical or super, super, super close. So we would say there appears to be no association. If you found that the type O was 44% in one and 92% in the other, and then type A was 10% in one and then 82% in the other, and then type B was 90% in one and 5% in the other, you'd be like, yeah, there does seem to be an association. Blood type B tends to be a higher percentage for having DAPT than no DAPT. So that is not the case in this one. There appears to be no association. So this one has all been filled out for us, and we're just going to answer some questions. According to the U.S. Census Bureau, of the 312.59 million people living in the U.S. in 2011, so remember this is 10 years ago, the number of people living alone is given in the two-way table below. So people living alone that are under 25, 1.45 million. Living with others under 25, 109.67 million. So let's think about that number, because if you look across the rest of the table, you'll notice this number is huge. Think about how many children who are living with their parents, they would qualify as under 25 living with others. Think about people that are in college or just out of college living with roommates. They would be under 25 living with others. And then you'll notice that the numbers get a little bit more reasonable, because now you're not including children and you're not including those people who are just entering the workforce. In each column, we have a total, the under 25s who are both living alone and living with others. And if you work your way across, you've got the total of all people living alone versus the total of all people living with others. And then the total 312.59, which were all the people living in the US in 2011. So what's the probability of living alone? So there are living alone 32.73 out of all 312.59 million, or approximately 10.5% of Americans live alone. What is the probability of being 65 or over? So 65 or over just means that you are in that category. This question has nothing to do with living alone versus living with others. So we would add together the 21.4 who are 65 to 74, and then the 17.76 who are also over 65, and they would be out of the total 312.59, or approximately 12.5% of the population are just 65 or over. What is the probability of being under 65? Well, what's nice, if you already did this over 65, we could use complementary events and say 100% of people are represented. If we take away the 12.5% who are 65 or over, that leaves us the other 87.5% who are under 65. What is the probability of being under 35 years of age and living alone? So under 35 and living alone would be the 4.16 here, living alone and under 35, and the 1.45 here, living alone and under 35. So I would add the 1.45 and the 4.16 together out of all 312.56 million people and get approximately 1.8%. What is the probability of being under 35 years of age or living alone? Key added the total number of people in the first two columns to the total number of people in the first row. What did this person do wrong? So if you are adding an entire row with entire columns, you end up counting some people twice. So this person counted the living alone and under 25 25 to 34 twice, because when she went across, or he, I'm not sure, went across that row, those two got counted twice because they also got counted in the columns. So if we refer to problem 10-6 above to complete the table below, we're looking for percentages. So what percent, sorry, I'll pull that down so we can see it. What percent of people under 25 are living alone? Now, when you fill in the relative frequency table, remember you're filling it in by columns. So we're saying in this first column, there were 1.45 million people out of that column had a total of 111.12. So that's approximately 1%, meaning that the other one is approximately 99%, because we're only talking about the under 25s, the total of under 25s living alone versus living with others. If we go to the next column, we had 4.16 out of that column's 41.57, which is about 10%, meaning the people in the living with others would be the other 90%. And you can go down and fill in the rest of the table doing the same process. And you can see my table here that's all filled in. Each one of the columns has to add up to approximately 100%. Okay. And when you fill in a relative frequency table, it is assumed that you will fill it in columns unless you are told otherwise. So if you had a table like this and the person said, if you're living alone, what is the probability, then you would go across and you would fill in your relative frequencies across. Unless you were told something like that, you will assume that you are filling in your relative frequency tables by column. Is there an association between age and living alone? Yes, there is. You will notice that as you get older, you are more likely to be living alone, right? It doesn't stay 10%, 10%, 10%, 10%. It starts increasing 13, 18, 22, 37. And you also could say that the probability of living with others decreases with age. That would be the other half of this statement. So there's a lot to take in here. We are not going to do this just in one day. So please make sure you come with questions.